regarding to today's topic, we are talking about what's it called workcard 1. So this is about Python automation. I think this is super helpful to data scientists because every time you're going to do a lot of work, right? So whenever you do a lot of work, after this today's presentation, hopefully everybody can get some tips. The speaker for today is Franklin. He is a co-founder and chief data scientist for a real estate data analysis company named Orion. And he was working as a data scientist in Facebook in their ads payments team. So he has a lot of experience on this data science, computer science kind of technologies. So let's welcome Franklin.
You guys hear me?
No.
No?
1 second, it's turning on.
All right, I can hear me. All right, cool. All right, guys, thank you for coming out today to listen to my talk. It's called Work Hard Once, Strategy and Automation Applied to Building Machine Learning Models. So, a little bit about me. It was mostly covered. That's my email address. Feel free to send me an email after this with any questions or comments or anything like that. Basically, the summary is that building machine learning models from data ingestion to productionalization is challenging with many steps, and of all the steps, feature engineering is the biggest differentiator between models that work and models that don't. Using automation and strategy, we can remove some of these challenging parts and focus on the main area of machine learning that adds the most value, feature engineering. I want to start by talking a little bit about John Boyd and the OODA loop. Is anybody familiar with this? Looks like get some yeses. All right, cool. So the OODA loop is the decision cycle of observe, orient, decide, and act. And it was developed by a military strategist named John Boyd, and he applied the concept to combat operations. So what it's used mostly for now is learning and commercial operations, and basically just moving faster and understanding and breaking down the steps in order to make better decisions faster. The approach favors agility over raw power in dealing with human opponents in any endeavor. So this is from Wikipedia. This is the diagram here, and as you can see, the blue section is the orient section. That's the most important part. So we start with observe. This is where all the external data comes in. So everything that's going on that you can observe is coming in that step right there. All that information goes into the orient stage. From there, you can make your decisions, and the feedback loop goes from the decide hypothesis, and you can go back to observe, you can go back to orient, you can go back through all the stages, but then you finally make your decision and act. So orient is most important. Since one is conditioned by their heritage, their culture, existing knowledge and learnings, the mind combines fragments of ideas, information, conjectures, impressions, etc. to generate our orientation. How well your orientation matches the real world is largely a function of how well you can observe. So we can basically use the same idea and apply it to the stages of machine learning. And The observe section is represented by getting the raw data from SQL, CSVs, APIs, wherever we get our data. Start to clean it, we're still in the observe section. And then we get into the orienting, and that's the feature engineering and the model training. Once we build the model, we evaluate it, that's when we can decide, and then we act, and that's the deployment. So of all of this stuff, I mean, probably 80% of the energy should really go into feature engineering and model training. And the way we can do that is by automating a lot of the other steps. Here's one. So I was talking with a mentor of mine from Facebook, and he was coaching me a little bit on model building. And I was telling him a little bit about our specific problems and the domain and the challenges we were having. And basically what he kind of came back to was we need to focus on data quality and data volume. And the more that we can have breadth of data, basically like features and columns and all sorts of breadth of data, and then depth is just number of rows, like how much data can we really get. Basically addressing these two things would take our feature engineering to the next level, and thereby taking our machine learning to the next level. Just touching on the observe stage just very quickly, my favorite tools for automating the observe stage are using Docker. That way you have a repeatable and reusable build environment, so you don't have to worry about building something that works on your machine and then it doesn't work on the server. You can't give it to anybody else. Nobody else can recreate your results. Jenkins is a nice automation tool where you can just automate pipelines and get stuff to run on cron jobs and things of that nature. And then Luigi, which is an awesome Python package for creating data pipelines themselves and chaining them together. So now we're at the Orion stage. We're at feature engineering. This professor said that coming up with features is difficult, time-consuming, requires expert knowledge, and applied machine learning is basically feature engineering. Xavier Connor said, the algorithms we use are very standard for calculators. We spent most of our effort on feature engineering. We're also very careful to discard features likely to expose us to risk of overfitting. Dr. Jason Brownlee said feature engineering is the process of transforming raw data into features that better represent the underlying problems to predictive models, resulting in improved model accuracy on the unseen data. So among all these experts, there's kind of a consensus that feature engineering is really the essence of what we should be focusing on. One more. So at the end of the day, some machine learning projects succeed and some fail. What makes the difference? Easily the most important factor is the features used. It's often also one of the most interesting parts where intuition, creativity, and the black art are as important as the technical stuff. So I have a code snippet here, and I'm going to step through it. And basically the question is, how do we iterate feature engineering faster? And for that, I like to use scikit-learn pipelines. We can create a pipeline that transforms with a final estimator, and the benefits are basically convenience and encapsulation. You only have to call fit and predict once on your data, and it fits a whole series of estimators. And safety, pipelines help avoid leaking statistics from your test data into the trained model, cross-validation, and ensures that samples are used to train transformers and predictors. So if we're using Pandas and we're starting with a data frame, we can start to stack these pipelines together and combine them using basically creating feature extractors. So this one is a data frame column extractor. And basically what you do is you start by giving it the column name from the data frame that you're starting with, and it pulls it out and then fills in all the missing variables, missing values in line 32 here. And then it returns you back the data frame as basically a column. This one is a data frame computer, and it takes the missing values and it calculates the median value and places that in place of all the ones that are missing. So again, we have a fit and a transform function, and same thing here, fit and a transform. This one is a standard scalar limit transformer, so we can just stack these, and you'll see later. But you can start by, basically what this does is it trims a scaled variable, which is like basically a z-score, from -3 to +3. And so anything outside of that range just gets set to the min or the max. So we're just kind of cleaning the data here. And then this is the pipeline itself. So in this line here, we're building a pipeline. So in this data set that I had, we had a column called square footage, and we had another one called tax assessed value. And so what we do is we do the data frame column extractor, and we pull out that column. We impute the missing values with the median for the square footage. Then we do the scalar, so we convert all the square footage values into scaled variables. And here we take the min and the max, and we trim them to those values. So we do the same thing again here for the tax assessed value. And then down here we use a data frame feature union, which is going to chain together these two pipelines. And then we can use a fit transform, and it's basically going to call all these functions in a chain. Then down here we can use the pandas concatenation function, and we combine the original data frame that we had with the new features that we've just developed, and then we return it. So, in summary, using automation and strategy, we can remove some of these challenging parts, and we can focus on the machine learning that's the most interesting, the feature engineering. And when we use automation and strategy to remove these challenging parts, and we can run through the glue much faster, generate better models, learn more about our subjects, and deliver more value. That's my email address. Are there any questions?
I have a question.
Yeah.
Yeah, so you're building all these pipelines, you have an input, you have an output. How do you test to make sure that pipeline works?
It's a great question. So you can build unit tests, and you can basically have a set data frame that you use to train, and then since you'll know the outcome that you want, you can basically create that in a certain part of the unit test and see if it matches what you're expecting.
Do you have any frameworks to recommend to do that besides just like the standard library unit test?
I use PyTest.
Okay.
Yeah, that's what I usually use.
Cool. Thank you.
Yeah.
I've heard that there's sort of like a popular notion in deep learning that feature engineering like maybe isn't as important. Do you agree with that, or not?
That's a good question. I don't really have an opinion on that, to be honest. I think it probably depends a lot on the classifier you're using. So I'm using a lot of gradient boosted decision trees, and so it's very important there. And I think deep learning has its own challenges, and it's probably a lot harder to implement in general. So, yeah.
I have the same question.
Okay. Yes.
How big of a data set are you dealing with when it comes to this pipeline?
Yeah. So typically, we have about probably 1 million rows. Yeah. So, and then we'll have maybe 50 different columns and 1 million rows, and then we apply these types of pipelines to them. And it might take, depending on the machine, a few minutes to run. Yes.
So, I mean, you call it feature engineering, but it was mostly filling in blank spots in the example. But how often do you come up with new variables like dollars per square foot, or taxes dollars per square foot, would have been something you could have come up with?
Yeah.
With those two, or do you typically leave it to the model?
No, that's a great point. I was trying to keep it a little bit simpler, but yeah, I mean, one of the things you can do is you can binarize variables, and you can do all sorts of stuff. Like you can derive fields. One of the things that I like to do personally is let there be more levels in the machine learning so that it can find the interactions itself. And I kind of tend towards I tend towards trying to start by adding all the variables in without necessarily adjusting them too much, and then seeing what the feature affordances are when they come back out. And then starting with those, and then see if there's like features that you can iterate on to build out from there.
So how would you consider this pipeline when you have different versions of the pipeline components? Like, for example, like you said, maybe first you add up some variables, but then maybe the next step you evolve your component function again. Maybe it's a linear combination rather than just a simple sum. Then you have different components, different versions that you check into GitHub. And now you want to build a pipeline automated, but then you check in these different components into the repository on different days. So I'm curious how you would track these pipelines.
Yeah, that's a great question. Another example that
Could you repeat the question? Repeat the question.
Okay, so that's a good. Okay, so the question was, once you start to check in some of these extractors and some of these pipelines into the code base, how do you make sure that they keep working later? Is it because you're saying that the data itself might change and it might not represent?
It could be and then the pipeline function components might change, right? Like maybe today you use missing values, you impute missing values with mean, and tomorrow you try to impute with mean, and then another you try to impute with some kind of regression.
Oh, okay. So you're saying like versioning of the
Right.
the extractors themselves. Yeah. So I would basically say that like I would use GitHub and feature branching, and then being careful about like what you bring into like the develop branch, and then what you bring into the master branch, and then doing versioning. So like putting tags on, on the, basically when you're at like a certain level in the master branch, putting a tag on it, and then depending on like, it's a good question. You kind of just have to, are you saying because like you're going to change basically the predict function later?
Like sometimes the same function, you have different implementation, and you just check into GitHub, right?
Mm-hmm.
And then some other times you might have different function names or function files, different Python files, and then you might use one or another. And then of course the data set might also evolve. Maybe the output requirements also change a little bit from week to week, perhaps. I'm not sure. Because you're trying to pull in maybe more data at the wrangling stage, right? And you keep expanding your features, increasing your depth, enhancing the data quality, so on and so forth. So there's many iterations and many perturbations to the data, to the code, to the version. And when you build one pipeline, sometimes you don't want to choose all the files or data available in the repository. You want to maybe select, a subset of the files only, so on and so forth.
Well, I would say my recommendation, so her question was about basically how do you make sure that the stuff is basically consistent across, versions of the modeling. And I would just say that that's like really a software engineering type problem. And you have to be careful, and you have to use Git, and you have to do versioning, and you have to make sure that even unit tests and things like that, just to make sure that you're doing stuff in a consistent manner. But yeah, I mean that's an important aspect to keep in mind. Just versioning and keeping track of it. Yeah. Yes.
Question. So let's say generally the feature engineering task is like feature reduction. So let's say you have m categorical variables and n numerical variables. Is there a systematic way to go about reducing the variables?
So I like to use principal component analysis, and yeah, I mean you can definitely play around with it, and you can basically create different groups of variables that you want to reduce the dimensionality for. So one thing that we might look at is there's like an estimated value, there's a tax assessed value, and then there's like a market value. You might have different estimates of the value. And so I might take, since those are all very highly correlated, I might take those and reduce them down to 2 or 3, principal components. Does that answer your question?
Yeah, somewhat, but how can you visualize that? Can you use something like a visualization?
I mean, you can do a scatter plot. You could do like one of the variables versus like one of the components. But yeah, that's a little bit more difficult to visualize since you're taking multiple dimensions, you know, maybe 5 dimensions and reducing them. But you could also do PCA1 versus PCA2, or yeah, you can just kind of play around with that. You could probably use a scatter plot.
Okay.
Yeah. Yes.
So if you have a Microsoft database, how do you get your pipeline ready so that you can extract all those data into it?
How can you create those features from SQL database without actually connecting to the database all the time? Like you're like, oh, I have one more feature, so now I have to rerun my 4-hour job again.
Yeah, that's a great question. So I use Luigi pipelines, and so I'll have one pipeline stage. So it's different than a scikit-learn pipeline. But it's just basically a Python class that you call, and it has state, and it marks itself done. And so I'll basically create the first query in the Luigi, and then it does like from a pandas, like it'll like read SQL, and then it'll save it as I can save it locally as a CSV file. And then the next stage can just read the CSV file. Yes.
So this is a bit above me. I don't do any machine learning or anything like that. But your core point is that you can use these pipelines so that you're always starting from scratch in your analysis with the raw data, adding columns, manipulating columns. And you can always go back to the raw data and start it all over again. Is that the point?
Yeah, and then you'll get the exact same answer every time. And that basically you can reuse a bunch of these components to very quickly add new features. And like his point was, you could have taken like square footage and maybe estimated value, and then have estimated value per square foot. And so like you would very quickly be able to just create another feature extractor that would pull those values out and do just a quick division, and now you have that.
So the advantage to you is that you're not storing any intermediate data and taking up tons of space or creating obsolete data sets that are going to sit around.
That's kind of an advantage, but I like to save all the intermediate files anyways. I think the biggest advantage is really that when you see the next data set and you're predicting in a week and a month, and you're doing it on the predict data sets, that it's consistent and coherent and predictable. And also that it doesn't break, because you can run the code once, you don't expect a certain type of variable or value for your variable, and the next time you get a null or a none value or a 0 or a -1. And so basically being able to handle these very easily so that the code doesn't break. Yeah.
So I saw you have a future scaling in your pipeline, but what if when you need to apply like random forest or the model which doesn't use future scaling, you have to create a new pipeline, or what would you do?
You can just not do feature scaling at all. Yeah.
Okay.
You could just skip that step, and you could comment it out, especially if you saw that it was having no increase in predictive power. Yeah.
Is there a way that we can create a template that, like when I open the model that doesn't require future scaling, I can just skip that automatically? I have to do it manually.
You could probably create like an if statement or something like that to handle that. Yeah. But yeah.
In the beginning, you mentioned Docker, Jenkins, and one more to
Luigi.
Luigi. Could you compare these three tools in maybe building a pipeline, and maybe from a data scientist point of view, who does not have the same level of sophistication in computer or software engineering, which approach might be better, or maybe a combination of the tools that could help build a reproducible modeling pipeline?
Yeah. So I think a good place to start is with Docker, because you basically get a reproducible environment, no matter if you're on a Mac or a PC or anything like that. So I think that's a good place to start. Jenkins is more like for doing stuff at a little bit more scale. Luigi is great for just basically chaining together Python tasks. So if you have one that was like read the data from the database, like that question, you could do that as a Luigi task. Then it will mark itself as complete, and then when you go to kick off the Luigi pipeline again, it will go back there, it'll see it's already done, and it'll just go to the next step. So I think those are probably the two best places to start.
So is a Docker usually takes up a lot of this space?
It depends. There's like a slim Python Docker image. I don't know how big it is, but it's probably pretty small. Yeah. Docker's a whole another like presentation. So,
Thank you.
yeah.
Are you going to post your slides and or code somewhere?
Yeah. That's a great question. Where should I post that?
Your page maybe?
Yeah, we're gonna post that into the meetup later.
Okay. Yeah.
And then I had another question. One time or a couple times I was trying to scale and do like standard scaling or another kind of scaling too, and it actually made things worse. What would you think? Why would that happen?
It probably depends on the classifier. What kind of classifier?
I think it was SVM, but I know that requires scaling. So maybe it was just the way the features were or something.
Yeah, that's a good question. I don't know.
So maybe the future is also related to all the future, and you want to scale all the features.
Yeah, maybe.
Yeah, that happened to me before. Let's get like the future, but later on I found out that like my score is really low. So later on I found out all the future, so they have some text to hit the relationship with the future I scale, so I have to scale over them, and it's quite cool.
Okay. Interesting.
Maybe you have some extreme outliers.
Yeah, exactly. Yeah, that's another case.
When I've used pipelines and feature unions in the past, sometimes it seems like they're a little hard to debug or introspect afterward, just because they can be very nested and you have to like use a bunch of methods to get to them. Have you found any like ways to get around that or tips for that?
Yeah, usually what I'll do, that's why I was saying that I like to save the intermediate files afterwards. I kind of like to inspect them by hand, especially if stuff is not working like I think it should. That's one place to start. Yeah, debugging is a whole another challenge for sure. But I would say it's one of the best benefits of like when you do get a successful feature extraction class, that like it is, it's something that you can like use as like a way to remember some of the gotchas and like how you handle null values or nones or zeros or like especially depending on like if there's certain types of numbers that you are expecting, making sure that like when you look at your data set that that's what you are feeding in. So basically like if you want to do like a min-max type piece of the pipeline so that you know that like the minimum value in there should be 0 and then you make sure that everything less than that is set to 0. Basically kind of like cleaning the data before it goes in to make sure that it comes out the way you're expecting.
Thanks. Sure.
I have one question. So you're talking about the automation and thinking as the data scientists need to do a lot of iterations, take a lot of time. So what about how do you handle the output? Are you going to build a database to actually output or send an email? What kind of like output you're expecting to?
So the question is, how do you handle the output from the predictive model?
Yes. Right.
So I think it depends. So a lot of what we do are batch predictions. So we'll predict over 100,000 or a million rows. So we typically will just save that back to the database. But if you're making one-off predictions, you can take a lot of the scikit-learn type stuff and you can pickle your model and then you can put it into like a Flask API and create an endpoint and then you can version it. And so you basically know like what your inputs would be for that, and then expected outputs.
I was wondering, like, on average, how much time would you spend on a future engineer? Because when I do project, it took me like a lot of time, and a lot of like top rate or people on Kaggle, they spend like 80% of their time on future engineering. To extreme, or how much time do you spend?
No, I think, so in a Kaggle situation, you have like basically the data set, and it's pretty clean. I think basically when you're spending less than 80%, it's because you're spending a lot of time on collecting the data, cleaning it, data engineering, DevOps type stuff, making sure that your server's running. So I think in an ideal situation, 80% is pretty accurate.
I thought I was doing something crazy.
No, I think, yeah, it really should be the focus.
Okay.
Yeah.
When you have 40 tables, and how would you approach the joining all those tables or database, which is inner join? But here, would it be Luigi or Pandas? And then second question is, how do you extract one-to-many features on a safe kind of side where you have 3 drivers in one car and you're trying to figure out some kind of feature on it?
Typically, so the question being around how do you handle joins between tables and one-to-many features? So typically what I've done is I've used MySQL databases and then basically created indexes on the columns that you want to join so that like the joins are pretty fast. And then I'll do that in the first step before I bring the data in. But I'm sure there's like a lot of different ways you can do that.
How can you join the SQL query into your Python pipeline, make it one pipeline? Is it possible?
I don't do it that way. I basically start with the data set that I want to start with and then add the features onto it. So I do the SQL and the joins beforehand.
One-to-many features, how would you have to recalculate the whole thing from the beginning?
Are these features that you're coming up with later?
Yeah, right.
Yeah, you might have to, but I'm sure there's like ways that you can do it in the code just with Python. I'm sure there's ways you can just to like do joins and basically take smaller data sets and extrapolate them out.
Hey, so I'm just kind of curious, sort of at a higher level, given your experience, have you found that there's certain aspects of, outside of feature engineering, are there certain aspects in your modeling workflows and frameworks that you find more work than it's worth to focus a lot on automation, and what might those look like?
I think the one of the most alluring and biggest time wasters is like grid search and basically trying to like fit hyperparameters over like huge spaces. I've set up EC2 servers, with like 16 cores and let them run for days, and then the stuff comes back and it's like the numbers are all over the place and they're not consistent. It hasn't found like a local minima over like a certain set. So I'm not saying that like you should never do it or anything like that, but I think for us, a lot of the issue that we should have spent that time on was cleaning the data, validating the targets, making sure that like the classifier, like what it's classifying on, we do like a true false, making sure that those values are actually accurate, spending human time looking at those and basically doing all sorts of like analytics around that, make sure those are consistent, and then I think kind of like the tuning a little bit, it goes a long way, and it's important to like test and make sure that it's consistent, especially with like if you're doing K-fold cross validation. That's super helpful to make sure that like across your data you're getting consistent generalized results. So I think that's like super helpful, but yeah.
When you have multiple models and maybe one model's output becomes the inputs of another model, so on and so forth, is there any special care we need to when we try to build the pipeline?
I don't really do that, so I'm not sure.
Could you talk a little bit about the importance of selecting the right algorithm? Maybe right algorithm is not the right way to say it, but the importance of selecting an algorithm versus the importance of getting the features right.
So are you talking about like using basically logistic regression or gradient boosted decision tree or different models? In my experience, the way that I've approached it is I've just kind of stuck with one, and I like gradient boosted decision trees. The reason I like it is because I like trees because it's a lot less sensitive to like scaling variables and stuff like that. If you do any sort of linear transformation on data and you put it into a tree, it's going to come out exactly the same way. So I think those are like a little bit more robust, and I like them for that reason. But I think in a lot of ways, like there's 12 different things that you can be focusing on. And for me, I think the data quality is first and foremost, and then the data engineering. Ideally, your data quality is not that hard to solve, and then the feature engineering is where you can be pretty creative and come up with a lot of insights. And I think basically iterating through the feature engineering kind of lets you come back to like the business question of like, why are we really doing this? What kind of things do like the clients know that are not being captured in the data set? What are the types of things that you can never know, like that are very predictive? For us, like for predicting like sales for homes, we'll never know like life events that are going on in people's lives. So we don't know if somebody like got a new job and they're going to move across state lines or something like that. So it's not something that I've focused on. It doesn't mean that like it's not a good thing to do, but yeah, I just try and like figure out like what I think will have the most impact and focus on that and spend most of my time on that.
Thank you.
So when you're in the process of getting ready to build out a new pipeline, the answer is probably a little bit both, but do you find yourself more often sort of sitting down and trying to flesh out what you imagine this entire process to look like in terms of, we want to make these, X amount of features, or is it more so, we're going to start somewhere and kind of see where we end up? What does that sort of look like?
Yeah, so one of the things that I like to do is basically do plotting and look at the response variable. So basically the thing that we're trying to predict, and compare it to like some of the underlying variables. And so create a histogram, for example, of like square footage, and then plot for each bin the percentage of the response variable. So we do like true false, so maybe it's like 2% for this bin and 8% for this bin, and seeing if there's like some delineation in the data. That's one thing I like to do. But yeah, I try and sit down kind of like with a blank piece of paper and just, or a whiteboard, and just kind of think about like what types of things do I think will be predictive, and then start to play with those and test those, and then build a feature and run it through. And I kind of try and go through pretty quickly and see like where there's feature importance, and kind of like looking at interactions, trying to look at plots where maybe you multiply one variable by the other, or take the log of a variable times the log of another one. Just like play around and try and just get an idea that way, and then just kind of like feed it through the machine learning and just see what happens.
When you say you use true false, does that mean the data's binary, or you're using a bit field to select your features?
Our predictive, what we're trying to predict is binary.
Oh, okay.
Yeah. So one of the things we try to predict is like, will they sell their house? And that's it. So we just kind of like reduce it down to that, and then we have all the different features. Yes.
You have given example, for example, imputations. This is very generic, but then oftentimes the feature transformation can be very dependent on the variable name. For example, some variable might start with missing values equals to 9999, and another feature might have missing values denoted as blanks. Now, we need to standardize the missing values before pushing this stuff into the imputation application component of your pipeline. But the problem is that before that, for example, we might have some code that are highly dependent on the column name. And that makes, whenever the column features changing names, a lot of, changes need to be made. I wonder if there's some strategy in maybe this pipeline that could help or...
Yeah, so I would make a column extractor for each column that has a different name, and then if you know that it's going to have different weird variables or values in it, then that's how I would handle it. Any other questions? All right, thanks guys.
Guys, I think Eric provided a tour after this session, so if you have interest, reach out to Taylor over there. Thanks for coming, and thanks for joining this discussion, and I will see you guys next month. Thanks, guys. Have a nice day.